Start. So thank you very much for attending. We're very happy to be able today to, do this webinar on this particularly interesting technology. So floating offshore wind. Just to start, a few words on us, on Enerdata. So we are a consulting company. Specialized in the field of energy and climate. For more than 30 years now, we have been providing different types of services using our expertise in the field of energy and climate, mixing a lot of different competencies and skills, notably on energy modeling, market intelligence, data science, and overall expertise in energy and climate. We provide with a lot of different services, so information services through databases that our clients subscribe to, but also customized services as well, together with different sorts of clients all over the world on producing energy scenarios, monitoring work, training. Business studies and various things in the field of energy. A few words on our speakers today. So my name is Quinten Chini. I will actually take a back seat here and just be sort of a host. I've been at Enerdata for now 7 years as a project manager, mostly working in the field of energy modeling. We also have with us Maëlys Castellan, who is an energy analyst, part of the Innovation and New Activity department. She has a background in geological engineering, as well as geopolitics of energy. She's been involved in various projects with us, mostly business intelligence projects, focusing on new technologies, but also contributes to various projects with clients on a lot of different subjects related to energy and climate change. We also have the pleasure of having with us Stefan Is, who is an independent consultant with more than 25 years of expertise, also in the field of energy and climate. Among other things, Stefan has been working with the IFPEN, so the French Institute for Petroleum and New Energies, and the Agence Française de Développement, the French development agency. His activity is focusing more and more on the floating wind. He's actually joined TechNip in 2008 and has been the vice president for renewable energy. For your information, TechNip has actually been the company that installed the first floating turbine in the world in 2009, and is obviously one of the leading company in the field of floating offshore wind. So without further ado, I will now leave the floor to Maëlys, who will present.
Sorry, this is my bad.
Sorry about this.
Yes.
All right. Yeah, okay. Maybe also a few words on the agenda first. If you can go to the next slide.
Yes.
Right, yeah. So just a bit of a few words on what we're going to actually present. So first, we'll give a bit of context on the role of renewables in general in long-term energy scenarios, and why wind offshore and offshore wind, and floating offshore, and more specifically, can contribute to supplying renewable electricity globally. We'll then make a deep dive into floating offshore wind as a technology, before exploring what is the actual technical potential of this particular technology globally. We'll have a Q&A session at the end. You have a specific box at the bottom where you can write your questions that you want us to address. We'll try to address as many as possible. Don't hesitate to start right away to type in your questions, and we'll address them at the end So now I will leave the floor to Maëlys for the presentation.
Okay, thank you, Quentin. So first of all, for this presentation, we will look at the role of renewables in long-term energy scenarios. So first of all, what is long-term energy scenario? Well, these are scenarios that go up to 2050 or 2100, and they are really projections that rely on a set of highly uncertain assumptions, meaning that different scenarios that are led or made by different experts within the world will end up with different images of the world in the future. But while these different scenarios, as we can see here on the right side of our screen, really differ in a long-term future, there's really a large consensus within the fact that in this future, electrification will become really important within the times, for example, by 2050. And for the aim of decarbonization of this electrification, the large consensus also goes within the fact that renewables will take over as the main source of electricity globally by 2050. As a whole, for example, in the most ambitious deep decarbonization pathways, renewable electricity generation is expected to increase by up to 8-fold by 2050. Now, a focus, for example, for Enerdata's scenarios that we have here. So these are the Enerfutur scenarios. We have 3 different kinds of scenarios. The first being the Enerbase scenario, which implies using existing measures and extrapolation of historic trends. Our second scenario is Enerblue, which adds on with realistic measures and really uses the alignment with the NDCs, the country's NDCs, and their emission targets. And finally, the Energreen scenario, which is a scenario in which is compatible with temperature increase below 2 degrees Celsius. And when we look and add on these different scenarios, for example, in graphs for analysis, for example, here in the bottom parts of those graphs here on the right, the CO2 emissions, we can see really when we add up these different kinds of scenarios, we can see that in a distant future, well, midterm, long-term future, for example, by 2050, we can see that CO2 emissions within time really change depending on what kind of scenarios we are based on. As I was saying before, so electrification will become, well, according to most consensus within the different scenarios that are elaborated by experts, electrification will be essential to reach ambitious climate targets. But this electrification will go hand in hand with renewables to reach these climate targets. For example, here on the graph on the left side, we can see the share of electrification by sector. So in comparison with today, 2021, and for example, the Energreen scenario, we can see that within all sectors, electrification will, well, all sectors are expected to be electrified by around 50%. And within the industry sector, the industry sector will be electrified by over 60%, really in our Energreen scenario by 2050. And so, well, as I was saying, to decarbonize our electricity, how will it go? We can see here on the right side of the screen, this graph that really sees the total abatement between the Energreen and Enerbase scenario. So how do we decarbonize our electricity? The main drivers will be, as we see here, well, the wind and the solar, so renewables as a whole. And so, yes, as I was saying, so renewables are expected to be a main driver in the future power mixes. For example, again, looking at, for example, 2030, 2050 in the different kind of scenarios. In the most ambitious scenario, so Energreen, we can see that renewables are expected to to fill up with around 78% of the global power mix in our scenarios, in EnerGreen scenario, while in the EnerBlue scenario, it will take up for 63%. Now, looking a bit more deeper, we can see, for example, in the EnerGreen scenario, wind is expected to take a share of 29% in the total global energy mixes. And when we look again with a more focused eye within the wind sector, we can see that onshore winds will take up for 74% by 2050, while offshore winds for 26%. Finally, just a few words about this map here. We can see the share of offshore wind within the energy mixes for the different countries within the world. And so now I can leave the floor to Stefan, if you want.
Yes. Let's, so I'll take the control. Is it working?
It should.
Let me see. So it should, up. Doesn't seem, yes. Okay, so what are the main offshore wind zone of development? So historically, offshore wind started in Denmark in 1981, if I remember well. By the way, this park is now has been dismantled in Denmark, and it was, in fact, fair to say that it was more an onshore wind with the foot weighted foot. Let's say, or foundation weighted, so because the water depth was not that important, and and as the time goes by, it became more and more important. As Quentin said, the first floating offshore wind industrial scale project has been installed by Technip in 2009. The project was led by Equinor in Norway, and it was installed in the south of Norway by 200-meter water depth. And in fact, bottom fixed offshore wind was limited by the water depth, and so for a certain while, the main zone of development were mainly located in Europe, in North Europe, in fact, and lately in China, with massive investment and massive project development there. But fair to say, quite limited, because in fact, in a lot of areas around the globe, quite often water depth, even close to the shore, water depth is quite important, and so bottom fixed offshore wind project couldn't be installed. And so what is important about floating is that it opens new areas to offshore wind, areas that were not thought to be a good zone of development. So what comes with this floating offshore wind new business is that offshore wind is now coming to new market where historically it wasn't able to go. And the main zone are definitely outside Europe, Asia, but also the US, in particular the East Coast, but also the West Coast. Next slide. Let's see if I can make this work. Wow. So as of today, the floating offshore wind is really a very niche market. So the very first floating offshore wind project, 2009, it was a 2.3 megawatt one and only turbine. Then in 2017, the high wind project was built in Scotland. It was around 30 megawatt project in front of the city of Peterhead in Scotland. And again, a 30 megawatt project. Then after, there has been this project in the coast of Portugal, Windfloat Atlantic, again around 30 megawatt, the first ever project, finance-based project. And then the project again in Scotland, in Kincardine, 50 megawatts. So as of today, there is something like 200 megawatt installed, with the very last one project that has been installed by Equinor in Norway, with a 90 megawatt project with a water depth of around 400 meters. And so it's definitely a very nascent sector, but with a high growth. As you can see, what is expected is that by 2035, there should be something like 60 or more gigawatt installed, and so a very, very, very high growth rate. And in fact, as the time, if we were to show you the similar pictures back 2 years from now, so something like around 2 megawatts, this figure would have been far lower than that. So in fact, we are in a moment where globally more and more are confident that floating offshore wind will have a massive investment. And as you can see, in Europe, obviously, and the UK, with Scotland, for instance, to be one of the host country, but also south part of Europe, such as Italy, Spain, somehow France, Sweden in certain way, the US, and also Taiwan in South Korea, or Taiwan in Asia. And with this very high growth, what you can see also is that the typology of actors that are active in this field is very broad. So obviously you have historical players such as utilities that are in a certain way at ease with this kind of project, which are very capital intensive, and basically when you go offshore, you go it for quite big project, at least bigger than classical renewable onshore project, typically thousands of megawatts, sometimes even gigawatts or tens of gigawatts. So basically they are more at ease. And then also they have to acquire some new capabilities around floating offshore wind, but still it's an area where they feel more at ease. Then you have also oil and gas super major that see here an opportunity first to decarbonize their portfolio, their activity, and also they see also a way to get value out of their skills, the skill they have in offshore oil and gas development, and so a way to capitalize on this knowledge. Then you have also some IPPs, plus some IPPs that which is quite classical in renewables, but here still you have some specific skill to acquire. Some also investment company, some financial-based company that are here because basically in the renewable space there is or in the financial space you have this this tendency to lack of project, to see a lack of project, and so you see more and more companies that are financial companies that are starting to be involved into project development in order to feed their pipeline of project and to be able to finance and finally bring project to life. So a large spectrum of actors. And last but not least, also you see here some EPC contractors. So as you know, in the offshore wind business, you need to have high-skilled EPC contractors, and some EPC contractors are even involved into the development of project, which is something that you do not see so often, and definitely this is the case in floating offshore wind. Do not know how I can make this move forward. Yes. So in terms of technology, you have basically three types of, in fact, four types, but more or less, it's almost three types of floating foundation. So basically, the wind turbines are not specific to floating, so the bottom fixed or floating offshore wind turbines, offshore turbines are more or less the same, not more or less, they are the same. And as far as the foundation are concerned, definitely it's different. So the main technology that are used are coming from the oil and gas sector. You have the spar, which is somehow a long pencil buoy with sometimes a large draft. For instance, the Hywind project, the very first project that Technip installed in 2009 was of that type, and with a draft of 100 meters. You have the so-called tension leg, TLP, tension leg platform, where the stability of the structure is ensured by tendons that are anchored onto the seabed. And you have semi-submersible, which are structures that are semi-floating, let's say, and barge are also can be assimilated to semi-submersible. Each of those technologies have advantage and disadvantage, and a main difference with bottom fixed offshore wind is that in bottom fixed offshore wind, the main risk of construction happens at sea. So definitely when you install the foundation, but obviously when you will have to install on the top of the foundation the wind turbines and the nacelle and all the blades. In floating offshore wind, all those key operation, and basically the operation where you link the floating foundation to the wind turbine is happening in port, so at the quay side in the port, so in a protected area. And then when this connection is established, then you take the complete system and will go to anchor it at the final location place. So the kind of risk between bottom fixed and the risk profile between bottom fixed and floating offshore wind program is quite different. And between all those type also of bow or floating structure, you have also each time advantages and disadvantages. Yes. So today, as of today, the cost of the LCOE of floating offshore wind is quite high, something like between 150 maybe and 200 euro per megawatt hour, based on historical project. Today, on new project, if you have to take some vision, you can extract the value that are coming from the French tender, ongoing French tender for 250 megawatt project that are still ongoing on the Brittany side and on the Mediterranean facade, and the selling price is around 120 or 110 euro per megawatt hour, and what the sector is anticipating is, as the project will install more and more machine, or more and more project will develop, the cost will drop, and what is expected is that the cost could be between 50 to 100 euro per megawatt hour. So basically, what the sector is anticipating is to follow a similar cost reduction curve as the one that offshore wind, bottom fixed offshore wind has seen. Voilà. Also, a main difference between the floating offshore wind in the bottom fixed offshore wind is the share or the breakdown of the capex, and one of the main issues is the weight of the wind turbine and the foundation. So in bottom fixed offshore wind, foundation could represent something like 30%, and the wind turbine something like maybe 50% of the capex. This situation is quite different in floating offshore wind, where the foundation is something like representing something like 75% of the overall capex, and the wind turbine only around 20%. So it's a big difference here, and also show you how far the EPC contractor behind those capex will be important, and will have much more responsibility in floating offshore wind than in bottom fixed offshore wind sector. Voilà. Another important issue on floating offshore wind is the environmental impact, but there is here a quite important. So you have in fact two stages of environmental impact: the stage of construction and then the operation. During construction, unlike bottom fixed offshore wind, floating offshore wind is expected to have less impact, and the main reason for that is the noise. In fact, the main environmental impact of bottom fixed offshore wind is the noise that you can produce anchoring basically, or fixing the foundation on the seabed, and using sometimes quite heavy industrial means. In floating offshore wind, you will, since you are not anchored into the seabed, you will have you will have less impact on noise, or you will produce less noise when you will install the anchor. Then obviously you will have during operations classical impact on birds, and potentially some impact also on marine life, and this has to be taken, but it's not expected so far to be that important. But fair to say also that we have mainly so far experience on bottom fixed, because you have up to more than 50 gigawatts of bottom fixed offshore wind installed around the globe, and you have only 200 megawatts of floating offshore wind installed. So as the time goes by, we will, and the sector develops itself, we will know better the impact of those infrastructure on the environment, and specifically on marine life. As key takeaway, first, I think that floating offshore wind is seen as the next growth driver for offshore wind sector, with more than 40 gigawatt currently in project and expected by 2030, and more than 20% of all offshore wind projects. So definitely it's a newcomer, but with a high expectation. The technology is breaking free from a water depth restriction, and allows to produce a massive amount of renewable energy in areas mainly outside of Europe, many different type of players are active in those in this area. As I said, coming from the financial world, but also EPC contractor, oil and gas, and utilities. So competition is tough in the sector. The expected cost of electricity should be around between 50 to 100 euro per megawatt hour, but still it has to be demonstrated. And given the scale of project, we are still here speaking about gigawatts and several gigawatts, and sometimes even more than that. There is a duty of diligence is required for the impact on the environment linked to the implementation of such a huge project. I hope this was interesting enough and understandable enough. I'll be happy to answer questions and leave the floor to the next speaker.
Yes, thank you. So for the last part of this presentation, we'll take a look at the global technical potential for floating wind. So here, first of all, we have a map of the world, which illustrates the different potential for floating wind, but also for fixed offshore wind throughout the world. So first of all, we can see in the purple kind of spots, the areas where technically it would be possible to exploit floating winds throughout the world. And in light blue, it would be for fixed offshore wind. Next question is, how did we delineate those different areas? So we've been looking at 5 different factors. The first being that we've only looked at locations where wind speeds are over 7 meters per second annually for a 100-meter height. And so these areas were determined as technically viable for the exploitation of offshore wind. A second factor is, so we've seen for fixed offshore deployments, it would require water depths under 50 meters. And while for floating wind, it would be water depths between 50 meters and 1,000 meters in depth. So we've only looked at those areas between, so beneath 50 meters and 1,000 meters. The fourth factor is only considering regions less than 200 kilometers from the shore. And finally, excluded within this analysis is the isolated regions, so beneath 10 kilometers square. Then, using those different areas that were considered as technically exploitable for either floating wind or fixed offshore winds, we then looked at different parameters. For example, for areas with wind speed between 7 and 8 meters per second, we assume that turbine planting densities could be of 3 megawatt per kilometer square. And for areas where wind speeds are over 8 meters per second, turbine planting densities were assumed to be around 4 megawatts per kilometer square. All of this to say that thanks to these different elements, we were able to determine technical capacities for floating winds, particularly. So in North America, according to all of these different elements, there would be around 10 terawatts of technically, potential for floating winds. So 10 terawatts is only for, the US and Canada, excluding Alaska. Then for Southern America, it would be 3 terawatts. So that would be only Argentina, Brazil, Chile, and Uruguay. Then for Europe, the estimations got to 7.5 terawatts. Southern Africa, so South Africa, Mozambique, and Namibia. So these 3 countries, estimations go to 1.5 terawatts. Eastern Asia around 5 terawatts, and Australia 3.5, well, more or less. So these are really the potential for technically where it could be, well, where floating wind, sorry, could be exploited. Then looking a bit more deeper within different zones, for example, we took North America. So as I was saying before, so technically, offshore wind potential is really great and even bigger for while only looking at floating winds, where it is estimated to 13 terawatts. So this includes Alaska. And when we look really at the different opportunities, we can see that Canada has really the biggest share within this potential. Canada has around 7.2 terawatts of technically potential within its boundaries, well, within its coasts. And now looking a bit more like at the different political support that exists in those two different countries. For example, in Canada, so Nova Scotia province, which is located here on the map. So this province in Canada plans to have 5 gigawatts of offshore wind leases by 2030. So we can see that really political support for, well, here it's more globally, so it's for offshore wind, but is really emerging. And more particularly, and this is really the interesting parts, for example, the US just launched, I think it was less than a month ago, its floating offshore wind shot. So the US really has now the ambition to reduce the cost of floating offshore winds by over 70% by 2035 to reach around 45 per megawatt hour in cost by 2035, and also has the ambition to deploy 15 gigawatts of floating offshore winds by 2035 again. So that was for North America. Then now looking a bit more at South America. So as I was saying before, the 3 main countries which really have potential in terms of floating offshore wind are Argentina, Chile, and Brazil, but mostly here Argentina, because if we look really at the figures, we can see that Argentina really gathers nearly the equivalent to Chile and Brazil in terms of technical potential for floating wind. So 1.3 terawatts. And while for political support, well, those 3 countries really don't have yet political support in terms of floating wind, particularly, but mostly for their either wind or floating, offshore projects. For example, well, Argentina have the ambition to increase its wind and solar to reach 20% within its energy mix by 2025, and through its Renewable program, it will aim to boost the wind and solar via public tenders. Just a few words for Brazil. So Brazil really is starting to exploit, or has the plan to exploit, its offshore wind. So for example, they are planning really big projects. For example, OW is planning to implement over 15 gigawatts of offshore wind in Southern America, Petrobras 2 gigawatts, etc. So companies are really interesting themselves in those kinds of projects for offshore wind. Finally, looking at Europe, again, as we were saying before, there is large potential for either floating wind or fixed wind in Europe, as you can see here on the map. So again, the purple areas are really floating wind, and light blue are fixed wind. So the main opportunities for floating wind in Europe are located mainly in 3 countries: Norway, Denmark, and the UK. Norway leading the path with 2.4 terawatts. And while looking at political support, so European countries that have offshore potential are starting to really have targets in terms of offshore wind. So for example, Norway, which aims to reach 30 gigawatt by 2040. And as Stefan was saying before, so really in Europe, for example, floating wind projects are starting to emerge. So for example, a few days ago, the Welsh government approved a 100 megawatts floating wind farm. In this past month, for example, the European Commission accepted the financing of a French project also. To be honest, I forgot the name. I think it's a 250 megawatts project just by the shores of France. So many projects that are really emerging nowadays. Finally, a few words for the conclusion of this webinar. So as we were saying at the beginning, so all long-term energy scenarios nowadays are really highlighting or going through a consensus that electrification will emerge within the world to come, and that renewables will really have a share, an important share, and an important role to play in the future. And this is also the case for wind energy, and more specifically, floating wind could become an important asset in achieving climate mitigation goals. This new technology, well, has technical potential, will have high technical potential, as we showed just before, for example, 7.5 terawatt in Europe, 10 terawatt in North America. So there is this potential, but then it is for example, for governments to have a role in creating the right circumstances for floating winds, for the market to develop via, notably, thanks to new policies or regulatory frameworks to be launched. And for example, well, this is the case with the US, which just launched its new floating offshore wind shots. So there is potential, and countries are starting to interest themselves in this kind of technologies. And finally, so yes, within the years and well, technical evolution and the rights frameworks developed, this new technology is expected to become more and more cost competitive over the next decades. So this is all for us. So I guess it's time for the Q&A.
Yeah.
Thank you. Thank you very much, Maëlys, and thank you, Stéphane. So I will lead the Q&A. There's a lot of questions. Thank you very much for that. Hopefully we'll be able to address as many as possible. So let's not waste time and let's get into it. So there's a lot of question on technical aspects of offshore, of floating offshore turbines. So I will try to group them together a little bit if you don't mind. So Stéphane, can you tell us a bit more on? Well, I guess let's start with two different aspects. The first one being, related to what are the actual limits in terms of water depth, and there was also a question on what type of installation vessels, if there are any that are needed to install wind parks. So that's quite technical. And also, if you can also give us a few thoughts on how really these turbines are compatible in areas, because we've seen that floating gives us the opportunity to install offshore wind turbines in areas that were considered too deep beforehand. But then you have the question of areas that are subject to typhoons and things like that. So if you give us a few elements.
Yeah. So about the water depth, the general idea is that technically you can install a lot of stuff even at very high water depth. The oil and gas industry demonstrated a real technical capacities and knowledge around this. As far as I can remember, I believe Technip has today the world record with maybe installation by 3,000 meter water depth. So the issue is not I'm not saying it's easy, yeah, but the issue is not technically the water depth, rather than how far it can be economically, or it can make sense economically speaking. So the issue is more an economic issue rather than a technical issue. So this is on the water depth. On the type of vessel, in fact, floating, as I said before, floating offshore wind is or let's say has a different risk profile if you compare it with bottom fixed offshore wind, and do not need so the jackup vessel that you can see, very impressive jackup vessel that you can see that are much needed to install bottom fixed or much needed for bottom fixed offshore wind project. And since all the critical operation with the construction or where the critical operation where you put the offshore wind turbine on the floating foundation happens at ports. So you have some tugboats, you have some, you need some tugboats, you need some also vessels to anchor properly the floating foundation, or to connect properly the foundation with the anchors, etc. With also take care of the connection, but even though those are specialized vessels, they are less critical than in bottom fixed, I would say, or let's say they are the fleet is more abundant and obviously costs less than those jackup vessels that you can see in bottom fixed project. Then the last question was about the typhoons. This is the new frontier of the domain, and floating offshore wind going to areas such as South Korea, Japan, Taiwan, that are much exposed to typhoon condition. The industry is now structuring itself to address those issues by first developing wind turbines that are so-called classified as typhoon class. So there is a typhoon class of wind turbine that is able to endorse a very high wind speed and to survive in those very aggressive environment. And as far as the floater is concerned, also the oil and gas industry demonstrated its know-how and its capacity to survive this kind of tough environment. And so it's all first a matter of design, and second a matter of, at the end of the day, of economics around it. So technically it should, the industry should be able to face it. Then how far economically it will be, it still can make sense. The industry will have to address this issue. As of today, there has been several prototypes installed. I mean, so-called typhoon-resistant prototype installed in Japan and installed in China, and so far they resisted quite well to harsh environment. So I would be quite optimistic on that issue, even though cautiously optimistic.
Thank you, Stéphane. Now maybe let's talk a little bit more on the potentials and the figures that you showed, Maëlys. I think there's a few questions that go in the direction of, you know, we kind of need to nuance the figures that were presented. Can you remind us of the key assumptions that were made, and maybe I mean, I can also speak on that a little bit, but maybe also when you're done, Stéphane can give us his opinion on, I think, more specifically on how do you, you know, you have high volumes of production that are located offshore. Sometimes you have a big potential in an area, but not a huge consumption center near it. So what are the technical solutions to address that, including maybe, I think there was a question on the possibility of having, you know, hydrogen to you know, transform the electricity into hydrogen to help with storage and that sort of things, and have more flexibility on that, but also in general how to supply this electricity towards consumption centers. So maybe first on Maëlys, a few words on the technical potential, and then if you have some thoughts on that, Stéphane.
Yes, so obviously,
no,
I mean, yeah.
No, I thought maybe Maëlys could perhaps speak a bit more on technical potential, and then you can address that question.
Yes, of course. So just a few words. So as I was saying, we did not do a complete study taking all the different factors within our study. Here it's really only the technical potential, looking at those 5 different factors that I've said just before. So really the wind speeds, the water depths, and several different aspects. For example, smaller regions where it would not be consistent not consistent, but really applicable to create large offshore wind parks near small centers with not much people, for example. And yes, considering afterwards, well, how did we calculate the potential? Well, yes, we simply assumed that for a different wind speed, we had to affect a certain turbine planting density. So really these different aspects, but we did not, for example, take, I don't know, other assumptions, for example, I don't know, technical problematics, as Stéphane was saying, for example, in countries where there are typhoon problematics, and these kinds of elements we did not take into account.
Stéphane, if you can add to that on you know the whole supplying the electricity. There was actually a specific question on, for example, Canada has a high potential, but mostly in its Arctic region, which obviously is a bit of an issue.
So yes, so you have to understand what drives the offshore wind and more specifically the floating offshore wind. What drives it is that in a lot of places you have a general need to have a clean power, but basically renewable needs to have places where you can install those wind power, those windmills, or those solar panel. And so basically going at sea is a way to recover somehow some territories where you can finally find what you don't have onshore, but there are places where definitely you have a lot of place, and Canada is definitely an area where onshore you have a lot of area that are available to install a lot of renewable energy. So how far offshore wind is really relevant for countries like Canada? This is a question mark, and the other way to answer this is that if you look at the situation of the US, the vast majority, or the area where you can install a lot of renewable is in the center of the US, and where is the population is at the coast, East Coast, West Coast, and Gulf of Mexico. So the idea, the problem also exists in some countries, even though they have some land available to install the renewable energy, still it can be far from center of consumption, and you have this issue of connecting. And this is where, in fact, offshore wind can bring, in a certain way, some kind of solution. Is quite often population are located nearby the shore, and you can produce the electricity that is needed by this population offshore. And this is typically, for instance, the case of Brittany in France. Brittany in France is one of the rare regions in France where you do not have any nuclear power. It's an historic situation coming from the history. And for a certain while, they were, as the population grew over there in Brittany, there has every winter some risk of outage. And so the Saint-Brieuc Park, offshore wind Saint-Brieuc Park, it has been planned definitely to, in a certain way, solve this issue and try to bring some solution of bringing some power for population living nearby the shore or living not so far from the shore. Yep.
Okay, thank you, Stéphane. So maybe a few words on because I've seen some questions on. So there are different figures to take into account. So there are these potentials. We've also shown basically a chart of the current projects in the pipeline to give an idea of what would be the installed capacity, for example, up to I think 2035. Maybe Maëlys, if you can get to that slide, I think it was earlier in Stéphane's slides, just to give a bit more elements of understanding on this particular slide. These are basically an image right now of the current projects with a particular status. I think it's in this case it's projects that have been approved one way or another. This is not a projections of how the capacity will actually be by 2035, because our assumption is actually that this particular branch, this particular technology is going to emerge. And this image could completely change with projects coming in the pipeline in the next years, right? So this is what we currently have and when it's going to be installed, right? So just to give a few words on that. So on top of that, you have the potentials that we've shown, but as we said, it's really a theoretical potential, right? With a lot of limitations to take into account. And I guess what is missing, even though this is also from one of our previous slides when we have a map of the actual wind offshore generation, is on top of the physical, supplying of the electricity from the offshore projects to the consumption centers. You also have to take into account that there's a bit of a competition between different technologies, especially renewable technologies. So not only do you have potential in areas that is going to be difficult to actually supply this electricity to the consumption centers, but there could be areas where you would actually prefer to install the onshore wind turbines or solar farms and that sort of things. So this is also a limitation in the type of in the actual development of the floating wind turbine and offshore wind in general. In comparison to the actual technical potential. So that's a precision that I wanted to add. Maybe one last question, because there's a few questions on, and I thought it was interesting as well, on the actual cost aspect of it. So you've shown a chart, you've shown actually two charts, so LCOEs, which is actually very highly depending on the wind speed and the actual area where the projects are based. There was also the structure of the CapEx, which is very different from bottom fixed and floating. Can you say a bit more on the actual share of CapEx maybe versus OpEx in floating versus bottom fixed in terms of the structure of costs in general, not just the structure of CapEx? And a personal question that I had is, if you assume that the CapEx, if you include all costs related to a floating wind project, are going to be higher than bottom fixed, and how do you end up with costs that are relatively similar? Is it because this is higher wind speed, or in general, or?
Yeah. So you have to also keep in mind that the sector is pretty much still in its infancy, which mean that the experience that we have in this sector is still a little bit limited. But I would say first that it is expected that floating offshore wind may have more a load factor, somehow higher load factor. Yeah. I say that very cautiously because a common view is that since you are floating, you will go in water that are at a quite long distance from shore, which definitely technically can be feasible, but from an economic point of view, if you are very far from the shore, it means that you have very long distance cable, which will cost you a lot of money. So how far it's still realistic to be very far from the shore from an economic point of view. Not so sure, but still. And if you look at the very few projects where you can gather some data on, for instance, the high wind project. Last time I look at it, showed some very high load factor, almost 60%. So somehow the highest load factor ever seen on offshore wind project. So how far this is only because it's about floating or because the area is particularly good? This is a question to ask to potentially Equinor or other. And fair to say also that in France there has been this experience done on the Atlantic shore, Atlantic facade, and also they claim a very high load factor. So first, somehow you can expect maybe a higher load factor, and on the OPEX, I'm not sure how far. It's very difficult because very different from bottom fixed. Basically, you do not want to bring back to the shore, to the port, the foundation plus the wind turbine on the top of it. You do not do that, or even if ever you have to do that, it has to be very exceptional, because obviously it would cost you a lot. So basically, once it's at sea, you want it to stay at sea and as long as possible. And I hope, and for the details of the calculation and how far the result can be potentially challenged, I encourage those who are interested in that to look at the document that has been used as a reference. So the reference is given in the chart.